Alright, so this is going to be the final review problem number 4, which reads, find the voltage drop across each resistor and the current through each resistor for the circuit shown below, and asks for what is the power of R3. So, in order to solve this problem, I've drawn the circuit a little bit bigger. Hopefully it's a bit easier to see like that. And what we're going to do first, probably the most useful thing, is to make a table, which we've done in class before, I know, where we have the voltage, current, and resistance at each point in the circuit. So we're going to have the total across resistor 1, 2, 3, and 4. Alright, so this is our table here. And then we can do our work over to the side here. So first what we have to do is calculate the total for all of these. And so we know that the total voltage is going to be 24 volts because our only power supply is 24 volts. So we can mark that as our total voltage. And then the second thing that we can do is to calculate the total resistance of the circuit. And we know that resistance to these equations, or according to these equations, will be the sum of the resistors in series plus the sum of the resistors in parallel. Now parallel is a little bit different in that we have to use the reciprocal equation, which we've learned, as opposed to just adding up the sum of the individual resistors in the series like we can for the first resistor here. And so our total resistance, or RT, total resistance, is going to be equal to 100 ohms, since that is the resistance of our first resistor here in series, plus we have here is going to be 1 over, and then again, this is going to be a sum of 1 over 180, which is this is R2 here. I should mark these. This is R2, this is R3, this is R4, and this is R1. And so R2 is 180 ohms plus 1 over 225 ohms, which is resistor 3 here, plus 1 over 95 ohms, which is resistor 4. And so what we can do is we're going to add up these reciprocals, so 1 divided by 180 plus 1 divided by 225 plus 1 divided by 95, which gives us a decimal here, a decimal. And then what we're going to do is we're going to take 1 over that decimal per our equation up here for parallel, and that is going to give us 48.72 ohms of resistance for this parallel section here. And so what we can do now is we can add this to our 100 ohms, and so that's going to become that. And so what we now have for our total resistance is 100 plus 48.72, or 148.72 ohms for our total resistance, which we can then write in our column right here. 2 ohms. Okay, now we can use Ohm's law, V equals IR, up here, in order to solve for the total resistance of the circuit. And so what we're going to do now is we have 24 volts, V, equals I, times 148.72 ohms. Or in order to solve for I, we then have 24 divided by 148.72, which gives us 0.161 amps, which we will then write over here, 0.161 amps as our total current in the circuit. So now that we have that, we can go ahead and we can fill in all of our known information about our resistors, which are given here. So we have 100 ohms for resistor 1, 180 for resistor 2, 225 for resistor 3, and 95 for resistor 4. So we have our resistances here and we have our total voltage here. Now, what we know is that because this resistor here is in a series circuit, that the current across that series circuit is going to be the same as the total current in the series, since that's a property of series circuits. So we can say that this is equal to 0.161 amps as well. And then once again, using Ohm's law, we can calculate the voltage across resistor 1. And so that's going to be 0.161 times 100, which gives us 16.1 volts. 16.1 volts. Now, what this means is that for the parallel circuit, that we will have 24 minus 16.1 volts remaining, or 7.9 volts across each path, since we know that from one end of our power source through the circuit to the other end of the power source, all 24 volts must be used. If we've used 16.1 volts across the first resistor, and we can only take one of each of these pads back to our power source, we know that the voltage across each one of these resistors has to be 7.9 volts. So we can go ahead and add that in here. So now that we made a table with all of our known information, we can use Ohm's law to calculate the current for each of the current across each of the resistors in parallel here. And so we have 7.9 divided by 180 ohms, which gives us 0.043 amps. The same divided by 225 ohms, which gives us 0.035 amps. And then finally, 7.5 divided by 95 ohms, or 7.9, divided by 95 ohms, which gives us 0.083 amps. And that gives us our total amperage across, or our total current, which is also the same as amperage, across each one of these resistors. Now finally, it asks for what is the power of R3. And by power, we are looking for watts, which is this equation written up here, W equals V1. W is power in watts, V is voltage, and I is current. And so if we're looking for the power across resistor 3, we can take the voltage here of 7.9. So W equals the voltage, 7.9 volts, times the current there, so 0.035 amps. And that is going to give us about 0.2765 watts, which is our unit of power. And that's all there is to question 4. If you'd like to, you can also calculate the total power of the circuit by using the same watts equation. You can also look and you can calculate it for across each of the resistors as opposed to just resistor 3, which has been done for you if we look in the back of our packet here. We have the total chart with everything filled out, R1 through R4, as well as the totals, and we have the power calculation for each of these. Again, depending on your rounding, you may have slightly different answers, but as long as you're in the ballpark, you are correct in terms of calculations.